Hello and welcome back to the beach. What we're looking at today is regression analysis part 2. So make sure you've had a look at regression analysis part 1 before you come on to this, because this one does follow on from it. And what we're going to do to start with is we're going to say, looking at regression analysis part 1, we came up with a load of numbers, and yeah, the numbers look really cool, and they came up with an understanding of what we think the relationship will be between two different variables. But how good is that type of relationship? Now, just as a very brief recap, what we found in regression analysis part 1 was that B equals a number and A equals a number. Remember, in this situation, A was my fixed costs. That's my total fixed cost. The total fixed cost should have been $10,000. It was really $9,250 when it came up in my regression analysis. B, my variable cost per unit. The regression analysis came out and gave me a figure of $6.25 per unit, whereas we'd actually fudged the numbers to make sure that they were supposed to be $6 per unit. So we do have some differences there. Now, there are two things we need to look at. We need to look at the impact of these differences, and then we also need to have a look at the relationship between the total levels of production and the total costs. And the total cost will be a mixture of our variable cost and also our fixed cost added together. So that's the type of thing that we're going to be looking at in a little bit more detail. So I'm interested in whether or not total levels of production and total production costs are going to have some sort of relationship to each other. Instead of just saying they have a relationship, what we say is they are going to be correlated, which means that if you change one of them, the other one will change as well. So if you change one, the other one will change as well. So that's the type of issue that we're going to potentially have. If you have perfect correlation, so if you have perfect correlation, it means that one variable shows you the change in the other variable completely. It is 100% reliant upon it. So it is 100% reliant upon it. So the variables can be plotted on a straight line graph, all coordinates lying along that straight line. Remember our key assumptions from regression analysis part 1. We said that we do assume there is going to be a straight line relationship. So the way that we've looked at this to start with is we sort of said, yeah, we're going to assume there will be a straight line relationship. So we've assumed that there will be a perfect correlation between total production costs and total levels of production, which is what we've done so far, finding out our fixed cost and our variable cost per unit. However, what actually happens is all of the actual results do not fall on a straight line. There is an element of variableness away from the straight line. And what that variableness now says to me is you have partial correlation, which means, yeah, there is a relationship between total production cost and total level of production. However, there are other issues in here as well. And the other issues we are potentially looking at here would include things such as other variables having an impact. Oh yeah, well, it does make sense that other things will have an impact in here as well, such as maybe hiring new staff, potentially increasing or decreasing levels of production, to change maybe the learning curve effect. All of those things can now have an impact. So we have not just perfect correlation, which is where one variable explains another one completely, but we now have partial correlation, where there is a relationship, but there's something else going on in here as well. So there's another relationship that we haven't yet identified. Now, the other thing I need to talk to you about here, guys, with regard to correlation, we can have positive correlation, where if one variable increases, the other one increases. Give you an example here. If you have a situation whereby the level of production goes up, you would expect production costs to go up. There's positive correlation. As one increases, the other increases. Negative correlation, well, what tends to happen here is the number of times you want to play cricket, which would be a high number, will now mean that we don't get to play because it's going to be too wet. That now means that there is not enough sunshine. So the number of times we want to go out and try and play cricket in the sunshine is now going to have a negative correlation to the weather, because it always ends up raining when we try and play cricket. It's just one of those things. So negative correlation means that as one goes up, the other one goes down. So as the number of games of cricket we want to play increases, the number of hours of sunshine tend to disappear, because we all know that playing cricket is just really a rain dance. Okay, the other thing that we can do here with regard to this type of correlation is we can measure it from a statistical perspective. And the way that we can measure this thing is through a correlation coefficient. And the correlation coefficient is the Pearsonian correlation coefficient that we use. It is known as R. Sometimes you see it as a lowercase r, sometimes you see it as an uppercase R. I'm going to show it as lowercase to make sure it doesn't get confused with anything else. the R figure that you have will always be between +1 and -1. If you come up with a figure which is bigger than +1 or smaller than -1, you've made a mistake. That now means something's gone wrong. Okay, so what does this type of correlation coefficient actually mean? We'll talk you through what it means and we'll talk you through how to calculate it. So what it means is, if you've got a correlation coefficient which is positive, it means you've got an element of positive correlation. If it's negative, you've got an element of negative correlation. If you have a correlation coefficient and that correlation coefficient is +1, exactly +1, that now means you have got perfect positive correlation. If you've got a correlation coefficient of say 0.9, that now means you've got good positive correlation, but it's not perfect. It means it's partial correlation. So instead of having perfect correlation at +1, we now have partial correlation at 0.9. Okay, Ed, but it's not just the positive correlation you can have. You can also have negative correlation as well. And what we would potentially have here with negative correlation is an inverse relationship. So as one increases, the other one decreases. And there's my little blue line going in the other direction. So as the amount of variable X increases, the variable Y goes down. And there's my number of sunny hours and the number of games of cricket that we can potentially go and play. If you have an R figure of 0, it means that there is no correlation at all. It means there's no relationship. It means that anything that you're looking at is what we call spurious. It means nothing's going to happen. Okay, so we understand the idea of the +1 positive correlation, the -1 negative correlation. We've got an understanding of some numbers in between. Now what we need to do is try and find a way to calculate this thing. Now the way that we calculate our Pearsonian correlation coefficient, which is R, is through the following formula. Oh my word, what's he done? He's come up with another one. Yeah, this is even naughtier. Now, this now means that we've got an awful lot of these numbers already from regression analysis part 1, such as sum of x, y, sum of x, sum of y, sum of x squared, sum of x all squared. We've done all that already, but what we now need to do is we need to add in an extra column for y's. And what's going to happen is if I go into my number crunching within this type of column, we had the x column, the y column, the xy column, the x squared. We're now adding in the y squared column. And what this now allows me to do is I can take all of these numbers and then pop them into my correlation coefficient, my R calculation, to try and work out precisely what's going on. Remember that in this situation, n, which is the number of sets of data, will be 3. So n is 3. And using our calculation, which is going to be R equals all of that, what we now get is this calculation. So we get R equals n3 multiplied by the sum of xy, 684,500, minus sum of x, 600, multiplied by sum of y, 33,600, all divided by the square root of. And what I've done down at the bottom of my fraction here is I've tried to show you lots of different types of brackets so you can try and follow it through a little bit more readily. We've got n3 multiplied by sum of x squared, 140,000, minus sum of x, 600, all squared, multiplied by another 600. That then gets multiplied by n again, which is going to be 3, multiplied by the sum of y squared, which is calculated that as 337,135,000, minus sum of y, 33,600 squared, multiplied by 3 again. And what that now does is, if you want to pause it and crunch the numbers, guys, just to prove that it really does work, that'll be wonderful. And what that now does is it gives me a figure for R, which comes in as 0.979. This shows me two things. The first thing it does is it shows me that we have a positive correlation. Therefore, as one increases, the other increases. It tells me there's one increases, the other increases. Okay, so that's the first thing it says. The other thing it says is it's quite a powerful correlation. So it tells me that as one increases, the other increases. And it also says that it's quite a powerful correlation. But how powerful? How strong is this correlation? Well, what we now do is we come up with a different aspect. So we've started off with our correlation coefficient. We now go to our coefficient of determination. Oh my word, what's going on here, Ed? We take the R figure and we square it. That's it. That's all we have to do. So calculating R is a real nuisance. Calculating R squared is dead easy. Take the number, dump it in your calculator, and just put squared. Now, what this means is, even if you have negative partial correlation, your coefficient of determination will always be positive, because a minus, when you square it, will become positive. Minus multiplied by minus equals positive. Now, within our example here, we had total production costs, we had total levels of production in terms of quantity. We've got an R figure, which is 0.979. If you now square that, it comes out as 0.9586. We express that as a percentage, so multiplied up by 100%. And that now tells me that 95.86% of my total costs are explained by the change in production levels. So it tells me that 95.86% of my total costs can be explained in terms of the change in production levels. And what that now also means is 4.14 is explained by something else. We don't know what that something else is. But what it now means is if I was to use my A figure and my B figure from the regression analysis part 1 and then try to predict what my costs are going to be in the future, it means I'm only going to be a maximum of 4.14% out. That now means I can add in an element of contingency planning for that extra 4.14%. And that's where this starts to work from a forecasting techniques perspective, and it now allows me to make a really good quality decision in the future. That's amazingly powerful, and that's the usefulness of this type of thing. And once you get through to the end of this session, you think, yeah, I can see this being used all the time. It's amazingly powerful. It's really, really useful. Okay, Ed, that's brilliant. I get the numbers. I get the maths. I'm hammered the proverbial out of my Paul calculator, and it's got given off some elements of smoke now. So maybe we need to put the calculator down for a second. Let's have a look at the wordy bits. So regression analysis is brilliant. Regression analysis is brilliant because of the assumptions that it makes. And first and foremost, it assumes that we have a linear relationship. It assumes that y can be estimated with reference to only one other variable, which is x. You can expand that and actually have it with multiple other variables. Makes the model a little bit more complicated, but we can do it. I'm not going to go into that here, guys, because it does get very, very nasty. We do assume that past performance is a guide to future performance, which means that the way that we've done things in the past will always be the way we're going to do things in the future. If you've got a new machine, if you've got a new type of product, if you've got a new way of making things, your past data is going to be rubbish. So don't bother using it. If you're going to forecast outside your normal parameters, i.e. you're going to look at an increase in production that you've never seen before, or maybe a decrease in production that you've never seen before, that now means that your reliability of your past data is not going to be potentially very, very useful. And that brings me on very nicely to my last comment, which is the big, big, nasty comment. If you put rubbish into our model, you'll get rubbish out. So you must have good quality data on the way in. So you must have good quality data on the way in. Otherwise, I'm just going to give you a model which means nothing to anybody. And it now means that the decisions that you make will be bad quality decisions and your business now falls over. And we don't want that to happen. We want you to make lots of money and be uber successful because we want the world's economy to grow, etc., etc. Okay, that brings me up to the end of regression analysis part 2. I really hope you've enjoyed it. I love the stat side of things. He says, I'm going to go and play on the beach now, I think. Thank you ever so much for your time and attention, boys and girls. I'll see you all bright-eyed and bushy-tailed very soon. Take care and bye-bye.